Hello dear students, let us continue with our discussion on real analysis. So, we have seen the properties of modulus or the absolute value of real numbers. Let us see what is the concept of epsilon neighborhood, okay, or neighborhood of a point, or say this one epsilon neighborhood. So, in today's lecture we will discuss about bounded sets, upper bound, lower bound, etc. Okay, so before starting, let us just have a look at epsilon neighborhood of a point. Okay, let A belongs to R and epsilon greater than 0. Okay, epsilon is a real number which is greater than 0. Then the epsilon neighborhood okay, of A is the set, say let us write it as n epsilon equal to the set of all those real numbers which satisfy mod of x minus a strictly less than epsilon. Okay, this is called epsilon neighborhood of a point. Okay, that means so by our or this properties of modulus that we have done, we know that mod of x minus a less than epsilon, this actually means that minus epsilon is less than x minus a, which is less than plus epsilon. Okay, so that is a minus epsilon is less than x less than a plus epsilon. Okay, so this set epsilon neighborhood is basically the set of all those real numbers which lie between a minus epsilon to a plus epsilon. Okay, so a plus epsilon is somewhere here, a minus epsilon is somewhere here. Okay, so these real numbers which lie between these two values, a plus epsilon and a minus epsilon, okay, they form the epsilon neighborhood of this point. Okay, so in other words, it represents the points which are near to A. Okay. So, near means in the sense that the distance of those points from A is less than epsilon. Okay. Now, epsilon could be something like 100 also. So, in that case, say A, suppose if it is A is 0 and epsilon is 100, so this neighborhood will be all the numbers from 0 to 100, minus 100 to plus 100. Okay, so that's a large set. Okay, so it's not necessary that epsilon is always a small number. Epsilon is any positive real number here. Okay, so epsilon neighborhood is the set of all points in R which are at a distance less than epsilon from a fixed number A. Okay, so the number about which we are finding out the neighborhood. Okay, so that is called epsilon neighborhood of a point, right? Clear? So if we can try this exercise, if x belongs to real number such that mod of x minus a is strictly less than epsilon for every epsilon greater than 0. Okay, then this x should be exactly equal to a. Okay, so we had already done a similar thing, that is if 0 less than or equal to a less than epsilon for every epsilon. Okay, means a is a non-negative number which is strictly less than epsilon for every epsilon greater than 0, then a has to be 0. Okay, so we will use something similar to this here, right? So, solution we have x minus a, this is modulus, this is always greater than or equal to 0. Thus, by the given conditions 0 less than or equal to mod of x minus a strictly less than epsilon for all epsilon greater than 0. So, we will, if you remember, how did we do this? We did it this way: if a greater than 0, then we showed that there is a problem here. Okay. means the number a by 2 will be a number which is less than a, but lies between this 0 and a. Okay, so this contradicts the fact that a is less than every positive real number. Okay, that was the system. So here also we will apply the same system. If mod of x minus a is strictly greater than 0, then half times of mod of x minus a, this is also strictly greater than 0, and half times of mod of x minus a, this is strictly less than mod of x minus a. Okay, because their difference is half mod of x minus a, which is greater than 0. Okay. Thus 0 less than or equal to half times of mod of x minus a, which is strictly less than mod of x minus a. Okay, but this contradicts, that mod of x minus a is less than every epsilon greater than 0. Okay, so here we have got an epsilon that is half into mod of x minus a, okay, which is actually less than mod of x minus a. That is the thing, right? So this contradicts the fact that mod of x minus a is less than every positive epsilon. Hence our assumption is wrong. Okay, our assumption was mod of x minus a is strictly greater than 0. Okay, so therefore let me write it in next page. Therefore our assumption was wrong. Okay, our assumption was wrong. So that means mod of x minus a is actually has to be equal to 0. So this means x minus a equal to 0. Okay, so this that follows from definition. Mod a equal to 0 if and only if a equal to 0. Okay, so from there we can write x minus a is equal to 0, that is x equal to a. Okay, so if a number x is or if a number x satisfies that mod of x minus a is less than epsilon for all epsilon, then this number x has to be a only. Okay, there is no other choice, right? So this property will be used several times in real analysis. Okay, now let us talk about what is an upper bound of a set. Okay, upper bound of a set in R. Okay, so let a subset of R. Okay, a be a subset of R, and let a be a subset of R, then a real number alpha is said to be an upper bound of a if x is less than or equal to alpha for all x inside capital A. Okay, that means that is every element of capital A is less than or equal to alpha, Okay, then we say that alpha is an upper bound of the given set. Okay, say for example, say a equal to 1 to 5. Okay, then here 5 is an upper bound. Okay, 5 is an upper bound, right? Because every element of a is less than or equal to 5. Okay, x is less than or equal to 5 for all x inside capital A. Can you find out any other upper bound of this set? Can we find any other upper bounds? Any other upper bounds of this sets? The answer is yes, we can find out many upper bounds of this set. Say What about the number 5.5? This is also an upper bound of A. Okay, so please don't get confused that an upper bound has to be an element inside A. It's not necessary. Okay, there are many sets where the upper bounds, none of the upper bounds lie inside A. Okay, we will get those type of sets. So here in this case 5.5 is also an upper bound, is an upper bound here for this set. Okay, 5.5 is an upper bound. Why? Because x is less than or equal to 5.5 for all x belongs to A. Okay, every member of A, you just compare 1, 2, 5. Okay, everything is less than or equal to 5.5. So this 5.5 is also an upper bound of this set. Okay, say I take another set, something like minus 7, minus 2, 1, 2, 3. That way it continues up to say 1000. Okay, so what is an upper bound of this set? So 1000 is an upper bound, is an upper bound. Okay, 1000 is an upper bound of this set. Then say 1001, there is also an upper bound. Okay, upper bound. So how many upper bounds will it have? Okay, that you try to think. How many upper bounds can we think of? See, 1000 is an upper bound, 1001 is an upper bound, 1002 is an upper bound, 3, 4, 5, 6. Whatever number you take greater than 1000, it is always going to be an upper bound of this set. Okay, so this set has how many upper bounds? Actually, infinitely many upper bounds. Okay, any real number greater than or equal to 1000 is a upper bound of this set. So in this case also, any real number greater than or equal to 5 is an upper bound of this set. Okay, right. So immediately from the definition we can see this result. Okay, that exercise, or yeah, you can do it as an exercise, that if alpha is an upper bound of a set A, subset of R, then any number greater than or equal to alpha is an upper bound. Greater than or equal to alpha is an upper bound of the same set. Okay, of A. Okay, so this is a very straightforward result. Okay, let us try to prove it. Let alpha be an upper bound of capital A, then x is less than or equal to alpha for all x inside capital A. Okay, now let beta belongs to real numbers such that, so beta is a real number which is greater than or equal to alpha. Okay, then x less than or equal to alpha, and alpha is already less than or equal to beta for all x inside A, right. We already have we have already seen that alpha is an upper bound, so that means x is less than or equal to alpha for all x in A, and so from there and using this fact that beta is greater than or equal to alpha, right. So we have chosen a number beta which is greater than or equal to alpha, and immediately it follows that beta is also an upper bound. Okay, that means, see, I have written x less than or equal to alpha, alpha is less than or equal to beta. So by this transitive property it follows that x is less than or equal to beta for all x inside A. So beta is an upper bound. Beta is an upper bound. Okay. Beta is also an upper bound of A. So any number greater than an upper bound is also an upper bound. Okay, right. So if a set has an upper bound, it actually has infinitely many upper bounds. Okay. So let us try another one, or let us define something called lower bound of a set. So it's an analogous definition of a set. Okay, lower bound of a set. Let A subset of R then a real number alpha is said to be a lower bound of A if x is greater than or equal to alpha for all x inside A. Okay, that means every element of A is greater than or equal to alpha, greater than or equal to alpha. Okay, so if that happens, if every element is greater than or equal to alpha, then we say that alpha is a lower bound of the set. Okay, for example, say you take A as say 0, 1, 2, 3, okay, like that, okay, or let's say we are taking a finite set, then 0 is an upper 0 is a lower bound of this set. Okay, 0 is a lower bound of this set because x is greater than or equal to 0 for all x inside A. Okay, 0 is a lower bound. Any other lower bound? Minus 1 is a lower bound. Okay, is a lower bound. Okay, why minus 1 is a lower bound? Because minus 1 is less than or equal to 0 and 0 is already less than or equal to x for all x inside A. Okay, so ultimately we can write therefore x is greater than or equal to minus 1 for all x inside A. Okay, so minus 1 is also a lower bound of this set. So in fact any number less than 0 will be a lower bound of this set. Okay, so here also we have an analogous result that if alpha is a lower bound of the set A subset of R and beta is less than or equal to alpha. Okay, beta is a number which is less than or equal to alpha. The corresponding result for the earlier case was if alpha is an upper bound of A, then any number greater than or equal to alpha is an upper bound. Okay, so here we will show that any number less than or equal to alpha is an upper bound. So if alpha is a lower bound of A, a subset of R, and beta is less than or equal to alpha, then beta is also a lower bound. Okay, beta is also a lower bound of A. Okay, lower bound of A. Okay, so solution is very simple. Just as I have shown, since alpha is a lower bound of A, so alpha is less than or equal to x for all x inside capital A. Okay, x greater than or equal to alpha is same as writing alpha is less than or equal to x for inside A. Okay, now let beta belongs to real number such that beta is less than or equal to alpha. Okay, beta is a number which is less than or equal to alpha. Then what do you see that? Then we see that beta is less than or equal to alpha, less than or equal to x for all x inside A. That is beta is less than or equal to x for all x inside capital A. So therefore beta is an upper bound, beta is a lower bound. So any number less than or equal to alpha is a lower bound of this set. Okay, so if a set has a lower bound, it actually has infinitely many lower bounds. Okay, so that is why we always say a lower bound. Okay, so it's not like the lower bound. So lower bounds and upper bounds, they are not unique actually. Okay, so we will write this as a note that lower and upper bounds are not unique. Okay, lower and upper bounds are not unique, Okay, right. Next we will see the definition of a bounded above set. Okay, bounded above set. Okay. So under what condition a set is said to be bounded above? Okay, so a set A subset of R is said to be bounded above. Okay. Is said to be bounded above if, okay, so it is said to be bounded above if it has a upper bound. Okay, so if there exists an alpha inside R such that x is less than or equal to alpha for all x inside A. Okay, if this happens, then we say that the set is bounded above. Okay, means if we can find an upper bound. So this alpha is nothing but an upper bound. See the definition, alpha is nothing but an upper bound. So a set A subset of R is said to be bounded above if there exists an alpha in R such that x is less than or equal to alpha for all x inside A. Okay. Similarly, we have bounded below set, right. So a set capital A subset of R is said to be bounded below if there exists an alpha inside R such that alpha is less than or equal to x for all x inside capital A. Okay. That means every number of A is greater than or equal to alpha. Then we say that the set is bounded below. Okay. So we have bounded above set, bounded below set. Okay. And what is a bounded set? Bounded set means it will have both upper bounds and lower bound. Okay. So bounded set means a set capital A subset of R is said to be bounded if it has both lower and upper bounds. Okay. If there exists alpha comma beta inside R such that alpha is less than or equal to x less than or equal to beta for all x inside capital A. Okay. So here alpha is this alpha is lower bound, and this beta is actually upper bound. Okay. Upper bound. So a set is said to be bounded if it has both lower and upper bounds. Okay. Otherwise, it's not bounded. Right? Clear? So some examples of bounded sets already we have seen. Say for example this one, A equal to 1, 2, 3, 4. Okay, this one. This is a bounded set. It has both lower and upper bounds. Okay. As 1 less than or equal to x less than or equal to 4 for all x inside capital A. Right. This is a bounded set. Then something like B equal to the set of all those x in R such that 1 less than or equal to x less than or equal to 7. Okay, then this is also a bounded set, is a bounded set. Okay. So till now we have seen examples of sets where we are getting lower bound, upper bound quite easily. Okay, but many a times it may not be possible to get such sets directly. Okay, so the first question that arises is when is a number or when is a set said to be not bounded? Okay. So for that, let us try to understand what is meant by saying that alpha is not an upper bound of this A. Okay. Say suppose for example 1, 2, 3, 4. Okay. So if I write something like is say 2.5, is 2.5 an upper bound of capital A? Okay. Is 2.5 an upper bound of capital A? The answer is actually no. Okay. So how it is no, that let us try to explain. Okay. So we know that alpha is an upper bound if the condition this is satisfied, x less than or equal to alpha for all x inside capital A, upper bound of A, if x is less than or equal to alpha for all x inside capital A. Okay. That means every element of A is less than or equal to alpha. So alpha is not an upper bound, under what condition? Not an upper bound of A, okay, means that alpha is not an upper bound of A, means that there is at least one element which is greater than alpha. Okay, just it's ordinary plain English language. Okay, every element of A is less than or equal to alpha. Okay, so now if that is not satisfied, then we say that alpha is not an upper bound. So that is not satisfied means what? Every element of A less than or equal to alpha, this statement is false. Okay, so what is true? Its opposite, or its negation is true. So what will be the negation of this statement? Say I give you a simpler example. Say every student has scored, every student say in second sem honors, okay, second sem maths honors has scored 80%, okay, 80% in, say, suppose HS. Okay, every student in second sem maths honors has scored 80% is HS. So now under what condition this statement will be false? Please think nicely. This statement will be false if somebody can give me a student of second semester who has scored less than 80%, or means who has scored something other than 80%. Okay, so here I have written every student in second sem honors has scored, say let us just change it, at least, okay, has scored at least 80% in HS. Okay, so this will be false if I can find a student who has not scored at least 80%, okay, who has scored less than 80%. Okay, so something like that. So here our statement is, so this is a very plain logic. Okay, every say I say something like every student in a second sem maths honors is from Silchar. Okay, every student is from Silchar. So this statement, if it is true, is okay, but if it is false, then what does it mean? Okay, if it is false, then it means that our statement here is incorrect, right? Every student in second sem maths honors is from Silchar. Okay, the negation will be, no, there is some student who is not from Silchar. Okay, so that is what you have to understand. There is at least one student who is not from Silchar. Then immediately this statement becomes false. Okay, so opposite or negation of this for all is there exist. Okay, this is what you have to remember. It's a very important thing. Negation of for all is there exist, right? So so what will be the negation of this? Every element of A is less than or equal to alpha. Okay, every element, say x of A is less than or equal to alpha, or say like that. The negation will be negation. So somebody is saying that, yeah, every element of A is less than alpha. Every element is less than or equal to alpha. Now I want to disprove it. So what I will do, I'll try to find an element that is greater than alpha. Okay, right. So so what will be the negation? There exists an element x inside A such that x is strictly greater than alpha. Okay, the earlier statement was, original statement was, every element of A is less than or equal to alpha. Okay, but then its negation will be, no, there is some element here which is greater than, strictly greater than alpha. Okay, so now you observe carefully, alpha is an upper bound of capital A if x less than or equal to alpha for all x inside capital A, right? So we can, for your understanding, you can also write this statement as this: if given any x in A, x is greater than or equal to alpha. Okay, oh sorry, x is less than or equal to alpha. Alpha is an upper bound if given any x in A, x is less than or equal to alpha. Okay, right. So alpha is not an upper bound, not an upper bound. So when I say that alpha is not an upper bound of A, so what does it mean? This means if there exists an x in A such that x is strictly greater than alpha. Okay, so this is the meaning of alpha is not an upper bound. Alpha is an upper bound if every element here is less than or equal to alpha. Okay, so it's not an upper bound if at least we can find in one element which is strictly greater than alpha. Okay, so similar to this, let us also try this negation of this. Alpha is a lower bound of A if given any x inside A, x is greater than or equal to alpha. Okay, so what will be the negation? Negation will be alpha is not a lower bound of A, not a lower bound of A if there exists an x inside A such that x is greater than or equal to x is strictly less than alpha. Okay, so for the original statement, the condition was given any x in A, x should be greater than or equal to alpha. So its negation will be there is an element x in A such that x is strictly less than alpha. Okay, so that is called alpha is not a lower bound. Okay, so when is a set said to be not bounded above? Okay, so a set is not bounded above if it doesn't have a upper bound. Okay, if it doesn't have an upper bound, then the set is not bounded above. If the set doesn't have lower bound, then the set is not bounded below. Okay, and if the set doesn't have lower bound also, it doesn't have upper bound also, then it's an unbounded set. Okay, so these are the things about bounded set, unbounded set. We will also try to do a few more things, a lot of more things actually in this particular class. Okay, so for today I am stopping here. We'll just continue with another one, right, in the next class.